Okay, welcome you all once again in this second lecture on metric space. And in the previous talk, you have seen that how we can define a metric function or a distance function that is called a metric on a non-empty set, and by which we can calculate the distance between any 2 points in an arbitrary set, whether it is a set of sequences, set of numbers or set of functions or anything. So this we can define the distance between any 2 points. Now, in the last lecture we have seen that we can define the distance function or the metric d on the set of all real numbers, that is by dxy is equal to mod of x minus y, and similar in the same way we can define the function d on the set of all complex numbers in that dxy is equal to mod of x minus y, and we have seen that this d is nothing but it satisfies all the properties of a metric, and therefore d is a metric on R as well as on set of all complex number, and therefore x, the set of all real numbers with this metric d is a metric space, and say in the same way that set of all complex numbers with this metric d is a metric space. Now today we will see some other examples of a metric or a metric space, or some other examples on a non-empty set X of a metric. Now we see that let us take any non-empty set. Okay, any non-empty set you can take, and then we define a metric dxy. We define the metric dxy is equal to 0 if x is equal to 0, that is to say the value of dxy is 0 if x and y are the same, and the value of dxy is 1 if x is not equal to y. So in other way we say that what does it mean? What is the meaning of this one? The meaning is that all points, we can say that our points are eventually distant from each other. Okay, that is to say, here you can see that if you consider the point A and you can consider point B, the point C, point D, point E. So basically the distance, you see that the important thing is that we say that if they are different points, okay, then the distance between them is 1. Okay, 1 unit or whatever you say that. Okay, it is 1. If they are same, then the distance is 0. That's all. Okay, this is our way to define the distance between any two element in a non-empty set. And now actually, and this is your, so we can say that d is equal to this thing. See, the important thing is that here is that this way you can define a metric d, okay, and you will see that this d satisfies all the properties of a metric. How you can say that? Look, here is the important thing is that because dxy is equal to 0 when x is equal to y, and it is equal to 1 when x is not equal to y. In any case, whether x is equal to y or x is not equal to y, the value of dxy is either 1 or 0. So dxy is greater than or equal to 0. Okay, M1 holds. Second one is that dxy is equal to 0 if x is equal to y. Okay, so this one way. Or if x is equal to y, then dxy is equal to 0. So dxy is equal to 0 if and only if dxy is equal to 0 if and only if x is equal to y. Okay, this M2 holds. Now third one is dxy Okay, so dxy in any case you write like this, dxy. Okay, so we take suppose two cases. If x is equal to y, if x is equal to y, then dxy is equal to, we can say, because x is equal to y, so you can write yx. So symmetry holds. If x is not equal to y, then dxy, okay, dxy is equal to what? Is equal to 1. And it is same as you take the distance between any 2 points. So this is same as dyx, where x is not equal to y, then it is distance is 1. So it means that the symmetry holds. Okay, so the M3. Now what about the triangular inequality? So again you can prove the triangular inequality, that dxy is less than or equal to dxz plus dzy. Okay, so for this you have to take 2 points. Okay, you have to consider any 2 point x and y. Okay, if x and y are equal, so this is equal to 0. Okay, and then you have to think whether x is equal to y or not. Sorry, x is equal to z or not. If x is equal to z, then this is equal to 0, otherwise it is 1. Y is equal to z or not. If y is equal to 0, then it is 0, otherwise not. So in any case, this must be greater, this must be either 0 or 1 or 2, but this is always 0. In the same way, you can consider for different x is not equal to y, and then you will see that this D satisfies all the properties of a metric, and it is called a discrete metric. It is called a discrete metric. This is very important. Keep in mind, we always use this word, and we will always consider many examples with the discrete metric. So this is called a discrete metric on x, and the set x with the discrete metric is called a discrete metric space. So the set x with a discrete metric is called a discrete metric space. Okay, now you can see that from this one you realize that we can always define at least one metric on every non-empty set x. That is discrete metric. So whatever is your set of elements, we can always define at least one metric on a non-empty set x, and that is the discrete metric. Keep in mind. Now the question is that, of course, here is we say that dxy is 0 if x is equal to y, and dxy is equal to 1 if x is not equal to y. Can you think, instead of taking 1, if we write dxy is equal to 10, or we write dxy is equal to half, or we write dxy is equal to, dxy is equal to 0 if x is equal to y, and dxy is equal to 10 when x is not equal to y. Or we write dxy is equal to 0 when x is equal to y, and it is half when x is not equal to y. Or 1 over 3, or here we can replace 1 over 3, 4, 5, 100, 10, 20, 30, 40, anything. Will that be a metric? If I write like this, we define dxy is equal to 0 when x is equal to y, and any number greater than or equal to 0. For example, I take 100, or I take 1 over 2 when x is not equal to y. What do you think? Would this be a metric on x? Can you see in this way whether this dA is a metric on x? Check it. Definitely this would be a metric. Instead of 1 you can take any number here. But of course, if this is not true, if we write like this, dxy is equal to 1 if x is equal to y and 2 if x not equal to y. Okay, then this is not a metric. Why? Because whatever is x and y, it is, of course, dxy is always greater than or equal to 0. But dxy is equal to 0 if and only if x is equal to y. So if x is equal to y, dxy is 1. It is not 0. So it is not satisfying the second property, that is your M2 property, and therefore this is not a metric. So if instead of taking here is if this is okay, and if you replace this by any number, even then this would be a metric. But if you will replace this one, the first one, by a non-zero number, any non-zero number, then this would not be a metric. This is an important thing. So you can see that on any non-empty set X, not only this metric, you can define other matrices. For example, I mentioned this dxy is equal to 0 if x is equal to y, it is equal to half if x is not equal to y. So you replace this half by any number. So you can define many matrices. So you can define many matrices on a non-empty set X. But a particular kind of matrix where dxy is 0 if x is equal to y and dxy is equal to 1 if x is not equal to y, it is called discrete metric, and the set X with a discrete metric D is called a discrete metric space. Now we can see that, suppose we have defined a metric dxy is equal to mod of x minus y on a non-empty set X, on a real line. Okay. Now the question is, can we define another metric on R, set of all real numbers? So let us see, here is, let us consider x is equal to R, set of all real numbers, and define dxy is equal to mod of f of x minus f of y, where this f is strictly monotonically increasing function. Okay. If this is strictly monotonically increasing function, then we can dxy is equal to mod of f of x minus f of y. We can define in this way. And then you will see that this D also satisfies all the four conditions of a metric. Okay, this is very simple and I left it for your exercise. And note that the strict monotonicity of f is needed to ensure the positivity of D. Okay, so this is also metric. So now you have seen that we can define the usual metric, we can define different kind of discrete metric, we can define this kind of metric on R. So not only this, we can define many other matrices on the set of all real numbers. Okay, let us move little more. That is to say, from the set of all real numbers, we can move to the plane, that is R2. So let us consider the set X is equal to R2. R2 means a set of all points in the coordinate plane. Okay, and let us take x is equal to the coordinates of x, the point x are x1, x2, and the coordinates of point y is equal to y1, y2. Okay, x and y are any 2 points in X, and define dxy is equal to square root of x1 minus y1 whole square plus x2 minus y2 whole square. And this is the usual way So for example, you have this is point y and this is point your x. This is the plane. So here is the coordinates are x1, y1, here is the y1, y2. So these are the coordinates of the plane. And now the usual way which you have studied in your class 10 or 11, that if these 2 points in a plane, then you can calculate the distance between these 2 points by using this formula. Okay, and therefore because this is the usual way, and definitely this will satisfy all the conditions of a metric, because we have generalized, because we have considered the 4 properties which are satisfied by the all the distances. So okay, so this is the basically this is D is nothing but it is a metric on R2, and because this is the natural way, okay, to find the distance between any 2 points in a plane, and that's why it is called the usual metric on R2. Okay, and X with this D is a metric space, and it is called the usual metric space because we are considering the usual distance. Now we can verify very easily that this is a metric, this function, okay, dxy is equal to this function, okay, satisfies all 4 properties of a metric. Let us see how we can do it. We can say that let's take x is equal to x1, x2, y any point whose coordinates are y1, y2, z whose coordinates are z1, z2. These are 3 points in x. Okay, then it is very clear from the definition that because this is we are taking a square root, so because this is the square, this is the square, this is always greater than or equal to 0, this is greater than or equal to 0, the whole thing this must be greater than or equal to 0. So first property is always it is obvious that dxy is greater than or equal to 0, so m1 holds. Now see m2 means dxy is equal to 0. dxy is equal to 0 means that this square root is equal to 0. So this square root means equal to 0, it means that this term must be equal to 0. So this term equal to 0. Okay, this term is equal to 0 means because here is the square, here is the square, so both are equal to 0. So this is equal to 0 and this is equal to 0. It means that the x1 must be equal to y1 and x2 must be equal to y2. So if the coordinates are same, x1 is equal to y1, x2 is equal to y2, it means that x must be equal to y. So x must be equal to y. So dxy is equal to 0 if and only if x is equal to y. Now let us take the symmetry property, that is dxy is equal to dyx. So by the definition, dxy is equal to square root of x1 minus y1 square plus x2 minus y2 square. Okay, now because this is the square, so we can write this term as y1 minus x1 square, and this we can write as y2 minus x2 square, and then you will see that this is nothing but it is equal to dyx. So dxy is equal to dyx. It means that the symmetry holds. Now there is little bit tricky to prove the triangular inequality. So for the triangular inequality, we calculate first the square of dxy. Okay, because here is dxy is equal to square root of this thing. Okay, so instead of manipulating the square root, so better way is we can take the square both the side. Here you can see here is, so you take the square both the side, then the square of dxy is equal to x1 minus y1 square plus x2 minus y2 square. Then it is easy to verify. So we take the square of dxy, which is equal to x1 minus y1 square plus x2 minus y2 square. Now in the first one you subtract z1 and add z1, and then in the second one you subtract z2 and add z2 here. Okay, so then we can write in this one, And now you will see that now you can open the square. Okay, we'll open the square, then the square of this term is this one, plus square of this term is this one, and here is the square of this term is this one, and the square of this term is this one, plus 2 times this into this, so 2 times this into this, plus 2 times this into this, which is equal to this, and 2 I have taken outside. Now let us calculate, let us assume that this term x1 minus z1 is A, and z1 minus y1 is B, z2 x2 minus z2 is C, and z2 minus y2 is D. Okay, and then we use the fact that if A, B, C, D are any real numbers, then AB plus CD whole square, AB plus CD whole square is less than or equal to A square plus C square into B square plus D square. Okay, so this is what? This is AB plus CD. Okay, so it means that it is less than, this term is less than or equal to square root of A square plus C square into B square plus D square. So this whole thing here is dxy whole square, this is less than or equal to, this term is same as here, this term is same here, but this term is 2 is same as 2, 1, but this AB plus CD, so the AB plus CD, the square, this is square root of this one, so A square, so A square is this one, plus C square is this one, into C square, okay, into B square is this one, so B square is this one, plus D square is this one, and take the square root of whole thing, so square root of this and square root of, plus rest of the terms are same as before. Okay, so then you can take z1 is here, y1, and you, instead of taking this one, you take this term is here, so here it is, and this term you can write here. And then you see that if you calculate this first term, this is what? This is this term is equal to dxz whole square. Okay, this is by the definition is dxz whole square. This term, this one is dxz. Okay, so 2 times dxz, and this is dzy. So this is dzy, so 2 times dxz, and this is what? This is your dzy, so this term is dzy, so you will get this one. But the whole thing is, this is what? This is the square of dxz plus dzy whole square. So dxy square is less than or equal to dxz plus dzy whole square. Now take the square root both the side, you will get the triangular inequality. So this is the way to see to verify the triangular inequality for the usual metric on R2. Let us take here is another example of a metric on R2. Okay, so here is we see that we can define a metric. Again, we are considering x is equal to R2, and we are taking 2 points x and y in R2 whose coordinates are x1, x2, and the coordinates of y are x1, y1, and we are defining D, the metric, okay, on x in this way, that dxy is equal to mod of x1 minus y1 plus mod of x2 minus y2. What does it mean? The meaning is that, and then we will see that this D is nothing but it is a metric on R2, and it satisfies all the properties of a metric, and therefore x is equal to R2 with this metric is a metric space. Now, what is the meaning of this? The meaning is that here you can see that if you have this is your x point and this is your point y, the coordinates of this x1, y1, the coordinates of this are y1, y2. Okay, then the distance between x and y, so distance between x and y, this distance plus this distance. So we are defining the metric from here to here, it is same as from here to here. That is to say, for example, if you go by plane from here to here, okay, that is the usual metric. If you go by car, and car is moving in this way, it is going from here to here and then is going here to here. So that is the way. So this is also a way to define a metric, and therefore this is also a metric on R. And all the properties are very simple. Only for the last triangular inequality, you can see that dxy is equal to this one by the definition, and you add and subtract. Here is you can add and subtract z1, and here you can add and subtract z2, and then use the property of mod function. You will see that dxy is less than or equal to dxz plus dzy. Okay, and so d is a metric on R2. Now another metric, the third metric we are defining on the R2, on the space on the x is equal to R2. So how we define? We define, suppose again, so this is equal to dxy is equal to maximum of mod of x1 minus y1 and x2 minus y2. Okay, the maximum of this one. If we define the maximum of this one, okay, then we will see that this d is a metric on R2. Now what is the meaning? Meaning is that if again here this is your point x whose coordinates are x1, x2, and this is the point y whose coordinates are y1 and y2. Then as we have seen that this distance is mod of x1 minus y1 and this distance is mod of x2 minus y2. But what we are taking? We are taking the maximum of these two. So the maximum of these two is this one. Okay, it means that we are neglecting this one. So we say that if we are moving from one point, okay, and then we are a little bit going here and then we are going here. Okay, so we are neglecting this distance and we are saying that the distance between x and y is this one. So the small portion we are neglecting. And then we will see that it's very easy to see that the d is a metric, it satisfies all the properties. Okay, very simple way. Now the question is, can we say that instead of maximum, okay, if I take the minimum, okay, that is to say dxy is equal to the minimum of mod of x1 minus y1 and x2 minus y2. Would it be a metric on R x is equal to R2? Try. Whether this would be a metric on R2. Can you find any example? You will have to see, you will have to check. Very simple example, you can calculate very easily. Okay? You can calculate very easily that this d is not a metric on x is equal to R2. But if you consider dxy is equal to maximum, then it is a metric. You can see that very simple way that if you are going from one place to another place, okay, and there is some little bit zigzag and you are ignoring little bit zigzag, okay, then you can say, okay, I traveled from this point to this point is this much. But you cannot ignore the maximum length. Okay, the maximum length cannot be ignored. The minimum length can be ignored. So you can see that and you can find the example where I will see later, where you can see that the minimum, if we are replacing the maximum by minimum, then it is not a metric on x is equal to R2. Now you see that here is we have defined three different kind of matrices on R2, and of course beside these three matrices we can define the discrete matrix, because as I mentioned that on every non-empty set X we can always define a metric that is a discrete metric. So we have seen that at least we have defined 4 matrices on R2. So it is very clear that you can always define more than one metric on more than one matrices on a non-empty set X. Okay. So thank you very much for your attention, and I stop over here, and in the next talk we will see some other examples of a metric or a metric space. Thank you very much.